the best way to get you motivated is to give you some applications, some overview of some applications in the area of machine learning. These are just a few, not all of it. So for example, let me pick a few of these and explain what are these things. For example, automatic language translation, this particular one. For example, you are given a sentence maybe in English. Let's say, I learn machine learning. Let's say this is some sentence in English, and you want a program or a software that automatically translates this sentence to another language, maybe French, and vice versa, or maybe some other language, or maybe another language, maybe another language. There may be several languages. I want to convert text of one language to another language. This is called automatic language translation. And this get mature. The programs now are available due to the blessings of machine learning, particularly deep learning. The apps like these are available and getting improved more and more and more. And think about the impacts of this kind of application if available. you need not to learn anything. If you need not to learn other languages, for example, you may have a software and that gets you in line, get you communicated with each and every one, as long as the language of that person or that group is available in the package. And that is available now and is being improved, and more languages are being added thanks to machine learning. Image recognition, not just this text. Image recognition. Let's say we have an image and I want to know what is the category of this image. For example, if this image contains a vehicle, I may call that it's a vehicle image. If this image does not contain any vehicle, I may designate this image as a non-vehicle image. Or maybe, for example, if this image contains some object like person, I call that a pedestrian image, otherwise it's not a pedestrian image. There may be more than one objects available in the image, and the image categories are defined in a certain way. Well, doable, actually done, very tremendously, beautifully, getting improved more, thanks to machine learning again. One other problem related to it is object recognition inside the image. Rather than categorizing the whole image at once, we may have a lot of objects inside the image, and different objects may have different categories, and we want to know in a particular image what kind of objects are there and where are they in the image. And we may then want to track those objects in a video, maybe. Yeah, object recognition, object detection, object localization on image data, very powerfully done through machine learning tools, and are getting improved. Speech recognition. I want to build, for example, a virtual assistant. I want my assistant to just recognize my voice and act according to what I'm saying. So for example, I just ask my computer, for example, to open my email inbox and read the first email, or maybe the read email from ABC company. Then, there should be a program that actually understand that all that speech and convert it to the commands or text, or digitize it and then act accordingly. Or maybe I just want to convert my speech to text. I just want to speak up and automatic captions should be generated. For example, let's say I'm speaking right now in this video and I want automatically the subtitles should be appearing here. And one tool might be speech recognition, available and is getting improved. Traffic prediction. I want, for example, what's the trend of the traffic in the next joint, for example, a joint where the roads join. What is the trend of the traffic? Where is the traffic moving? Where will be the next blockage, if any? And where will be the fast track? where will be the density that is higher? Or maybe, for example, at a traffic junction, I may want to decide my signal timings depending upon the density of the vehicles on a road rather than the fixed timing. For example, let's say we have 2 or 3 roads that different cameras are seeing, and on certain roads there is some certain density of vehicles, on another road there is another density of vehicle, and so on. And let's say I want my traffic signal timings to adapt according to the density rather than having a fixed timing to optimize this kind of scheduling much more dynamically. Well, yes, people are working on that, and it's happening to a very initial level. For example, through machine learning tools. Product recommendation: you visit a particular website, you see certain products, you see accessories of those. Next time you go and visit maybe the same or the other website again, you get certain recommendations. From where? Movie recommendations, for example. You see certain movies, you are from a particular location. At that particular location, other people, they watch certain movies with respect to those, their interest, with respect to your localization and your certain data. Maybe people are recommending, or the website is recommending movie to you. This movie, maybe you're interested in watching that. Self-driving cars, the breakthrough. The people are working on this for example, right now this self-driving cars are really one of the main focuses of deep learning. And the kind of learning involved here is normally known as reinforcement learning. They want driverless driving. There are a lot of sensors, a lot of cameras, other sensors available on the car. The car should decide on its own where to move, when to change the lane, when to speed up, when to stop, and stuff like so. Whether emails are spam or not, virtual assistants, online frauds, stock market, health sciences, and whatnot. There are a lot of applications. And more the machine learning technology is getting improved. These applications are becoming more and more powerful and more and are gaining attention of people from industry as well as from academia much more, and this machine learning field is growing more and more. So you may be thinking, why this machine learning kind of thing, or in particular the data science or machine learning? Sometimes this data science and machine learning term, they normally used interchangeably. Although we can define different roles, that machine learning has this particular role, data science is a big umbrella in which machine learning is one component and stuff like so, but several times this machine learning and data science, these terms are used interchangeably. And you might be thinking that why at this particular time the data becomes so important? Why we are moving towards automating these kind of stuff in this particular time? Why not earlier? So yeah, there is a reason to it. So let me explain. For example, that right now there are certain things that has happened, and because of that, this machine learning or data science, it just become boosted. So for example, earlier, maybe a few decades before, powerful machines were not available. Even if you have a lot of data, you want to build a model that do a lot of processing for prediction, for the future things, for the future trends, what is happening, to understand data and stuff. You need a lot of processing power. And unless and until this fancy or fast hardware is not available, you are just stuck. But right now, this is really the case. The powerful machines, very fancy hardware, parallel computing, even clusters and clouds, they are available, making the processing power, computational power, increasingly available. And this is one reason of the boost in machine learning. This is one reason. The other reason is availability of large amount of data. All the applications that I've shown you, let me go back and show you a lot of, they all depend upon data. For example, this automatic language translation, to build a particular software or model, we will see what a model is. You need a lot of data a lot of data from different languages, and then you will be able to build a model. To build an image recognition system, for example, you need a lot of images, labeled and pre-processed images to get a model working. To get a speech recognition model, you need a lot of audio signals and their corresponding text and stuff like so. So you need a lot of data to build these models to perform very well. In earlier ages, for example, the amount of data that were available was not that large. So for example, unavailability of data, that actually was one hurdle in building these applications and building these models to perform very bad in a good way. So now, for example, the huge amount of data is available everywhere. There are cameras, they are sensing a lot of images, they are recording a lot of videos. Everywhere there are audio input sensors, they are recording audios. Your mobile phone, it is emitting each and every location of you, when you are moving where, on, for example, Facebook, WhatsApp, you're commenting, you're liking, you're doing a lot of stuff. Each and everything is being recorded. And these recordings, they are growing second by second. So a lot amount of data in the form of text, audio, video, a lot of these data, for example, is so it's available. So huge amount of data is available these days in several different formats. And now, as expected, people have powerful machines. They can process a lot of data, and a lot of data is available. So machine learning is a natural thing to increase, to improve, to get attention. Another thing is that because of the availability of both data and computational power, people tend to build a lot of software, very stable software. And the software stack, for example, the software stack is very much stable and available, and people are improving more and more. Due to availability, for example, a lot of software are available and they are very well tested, stable. A lot of features, very high level features, are available just to work in machine learning. For example, Scikit-Learn in Python, TensorFlow, Torch, Spark for distributed data handling, a lot of other libraries as well. So as a consequence, what is happening is the software stack is becoming more and more powerful. That gives rise to more attention of the people. The hardware people, they are actually building very powerful machines. Data is already unavoidably increasing. So all these things in a particular circular loop, they are actually getting this concept of machine learning, gaining the concept of machine learning, or to really higher levels, and the machine learning is getting much more attention these days. And all these things, they are happen just very recently. So that's why that's why the machine learning becomes much more important in these days. Although the mathematical concepts, the data, it was available earlier, and all the software stack, it is built upon the languages that were available earlier. But right now, it is really these three are the main factors that give rise to the popularity of machine learning. And it is assumed that this popularity will go on and on and on, and will improve and increase. So yeah, so let's dive in to see what actually machine learning is and how it utilizes data to actually build the prediction systems, the models that are capable of predicting what can happen in future. So let's dive in. Okay, so let's say, just to take an example, let's say you are given some images, maybe this image and this image. This image, if you see that image eventually is each color is actually represented by 3 numbers. So its red value may be 32, and green value may be 44, and blue value may be 15 or 150. Each location here, which is the location, for example, the row number and column number, that location, at that particular location, there is actually that color is represented by its code, and the code is what's the red code, what's the green code, and what's the blue code. So you can see, and sometimes called a pixel. You can see, for example, there are a lot of pixels, which means eventually that whole image is basically a lot of numbers. A lot of numbers. For example, if we just think this image as here, for example, a lot of numbers that represent all of these, they represent the red numbers. Then another matrix, for example, of numbers that represent the corresponding green values, and another matrix that represent eventually the corresponding values of the blue color. So if you pick, for example, any location, you get the 3 numbers. But I mean, I can rearrange all that 2-dimensional array stack to just one thin array, and eventually it will be containing a lot of numbers in a particular sequence. So at the end of the day, this image is actually a list of a lot of numbers. Similarly, this image, and that image. So given some data, so for example, this is a data sample. Let's say we relate a label or a category to that data. For example, this is a dog. Let's say this is a dog. So dog is a category or label for this. This is also a dog. This is a dog. And this is a cat, for example. This is cat, this is cat, this is cat, and so on. So if we just think as this first image as this vector of numbers, a lot of numbers, later we will see that these numbers are called features. These numbers, and let me denote this whole vector as x1, for example, then y1 might be dog. So y represents the label of this. x2, for example, which represents this particular image, may be a vector of the same length if the images are of same size, and y2 is also dog. So basically, data is given in certain applications. Data is given in the form of data along with, a sample along with its label. And the goal is to come up with a relationship of this sample to the label. So for example, we want to learn what kind of characteristics are there that defines this particular object as a dog, so that next time if we get an image, or maybe after having this knowledge, if we get another image whose relationship is not known, due to our previous understanding of this relationship, we get to know whether it's a dog or a cat or what. Okay, this is a classical example of supervised machine learning called classification, but this is just to give you that data actually is required. For example, if there is a kid who want to learn about, you want to teach a kid, for example, about this particular object, what will you do? You will somehow show this image to the kid, and then maybe speak and say it's a dog. The kid will grasp some pattern of this image and grasp another pattern to say that it's a dog. Okay, great. Then you show this particular image to the kid again, and you say it's a dog. Now the previous learning of the kid will maybe a different one, maybe of different feature. The kid might have learned that an object with a lot of white color is a dog, but after seeing this image, the kid will kid will see more patterns and more features that are specific to dog that are not based on color. So color might not be a good feature. You might be saying, okay, there may be two kind of black holes there. The kid may not know these, they are called eyes, but these are two black holes, and then something like so. Then you show this image and you say it's a dog. Then the kid will grasp more patterns, and then this is a dog. Then the kid will grasp more patterns, and so on. Then you might show the samples from different classes and their labels. And the kid over the time will start gathering the features that may define a particular group or may differentiate among the different kind of groups. The prior one is called the generative modeling, and the other one is called discriminative modeling. Either way, that's the whole story. I mean, if you want a kid to learn about cat and dog, you have to show varied pictures of dog. The dog can appear in what form in front of you. That will be a dog. You have to show it. And then the kid will start actually getting attention to what kind of features are there that define a dog, or what kind of features are there that differentiate between cat and dog. Okay, so a lot of data is available to train a model. Here kid is our model, and we are supplying a lot of data to train it. Once the kid is trained, then we can show the kid another image maybe and ask whether it's a cat or dog. And according to the learning of the kid will say, okay, it's a cat or dog, or whatever the learning pattern the kid has adopted. So that said, we might be thinking, what are the different kind of learning? What are different kind of learning? One is called supervised learning. In supervised learning, we show a lot of objects. We have a lot of objects, and for each object, we know the category of it. And we want to build a model. Just assume this model as model like a kid's brain, for example. So we show all the examples, a lot of examples, and along with the labels. And once the model is trained, then we show an example without label, and we expect the model to predict its category, because we have shown the similar kind of, not exact, but similar kind of objects along with the labels. So we are expecting the model to perform accordingly. Supervised learning has two kind of basic learning models. One is called classification, and another one is called regression. In classification, the labels, or what we want to predict, they are actually class categories. For example, different fruits. For example, mango, that's a class category. The apple, that's a class category. Cupcake, that's a class category. And watermelon, that's a class category, and so on. So the output, or what we want to predict, or the attribute that we want to predict, is categorical. Has a set of categories, and we want to predict a category. On the other hand, in regression, what we want to really predict is some continuous value. For example, just think about we want to predict the life expectancy of a particular light bulb. So we have a light bulb, we have a lot of features of the light bulb. For example, who is the manufacturer of the light bulb, what is the capacity of the light bulb, what is, for example, the material used, what are the attributes of the material used, and how long this light bulb is working in my organization. For example, it is working very well. And given all these attributes, let's say want to predict the life expectancy. For example, after 3 days. So maybe after 3 days from now, what will be the life expectancy of regression of my light bulb? So life expectancy might be in terms of time. How much time will it stay more? So that's a continuous value. That's not a category. That's a continuous value we want to predict. Maybe we want to predict, for example, depending upon a lot of attributes, for example, investment, how much investment we did in a particular business, and how much investment we did in a marketing, for example. These are attributes. And what are the areas we select for marketing, and what are the characteristics of the people on that area. And now we want to predict, for example, at what quantity we may need a particular product, because the demand may be at this particular quantity. So we may want to predict the demand based on several other attributes. And this demand is no longer, again, a categorical, it's a continuous value, maybe any demand, for example. So both the classification and regression model, they are there in supervised learning. And supervised because to train a model, you need to have attributes along with the label. If the label is actually represent classes, then that is called a classification data. If the label represent the continuous values for already available data, for example, in last year, what demand actually appeared in last year, and what demand actually appeared in last year. Let's say all that data is available. Now we know the attributes along with the previous labels, what has happened, and we fed all that data to our model, and then expect our model to do the future predictions based on these attributes. So that is supervised because the labels or the attribute that we want to predict is available on the given data, and that given data is sometimes called the training data. Okay, there is another learning method which is called or model which is called the unsupervised learning, in which, for example, the labels are not available. We do not know this particular object has what class label. We do not know this particular object has what class label, and so on. But we still want to group different objects together so that each group has a particular group properties that they share. For example, all these are all birds. We are seeing that these are all fish. We are seeing these, and these are all cats and dogs and stuff. So one kind of grouping might be on this behalf. We might have done the grouping based on color. So all the black objects, all the objects that have black dominant color, all the objects that has green dominant color, for example, that might be another grouping. After doing that grouping, or sometimes called clustering, let me write that term, clustering. After doing this grouping or clustering, so what we do not know is that what this particular object is, but what we know is that these two objects, they share certain properties. They are like same. And the similarity measure, on what grounds we are seeing these are same. Similarity measure is something, if you change the similarity measure, for example, if you say that the two objects are same based on color, then your similarity measure depends upon color. If you say that the two objects are same based on other characteristics, then your similarity measure. So how can you say them similar? It depends upon what similarity measure you are using, and changing the similarity measure to a different thing actually get you a different grouping. So this is unsupervised because we are available with a bunch of samples, but we're not available with their labels. What are their labels? Actually, if the labels are available, then they are already grouped. But the real goal is, given a lot of data, let's say we want to split the data or group the data into 3 groups, how can we go about that and doing that? So that is called unsupervised learning, and there are several models, there are several algorithms to actually achieve unsupervised learning. Another form of learning that appears, and get popular more recently is reinforcement learning, is that there is a particular agent, for example, who actually have to do certain actions. And in the environment, for example, if that particular if that particular agent do some action, obviously the agent can do a lot of actions. For example, action 1, action 2, action 3. There are a lot of actions that an agent can do. Agent can perform a lot of actions. The agent must decide based on a particular state what action to perform. Once the action is performed on the environment, number one, the environment changes and the agent observes the changes, so get the observation back. And based on the action, the agent may receive a reward that may be a good reward or bad reward, but we do not know that's the main difference. We do not know at a particular action what reward we get, whether that reward is beneficial or not at this particular point. And that is one difference between supervised learning and reinforcement learning. There is a particular goal. For example, if you're playing a game, chess game, for example, then there is a particular goal to achieve. But the moves you are making on the way, for example, you make a move, you get a pawn, so that's a reward that you get a pawn, and the observation is the new board position. But that reward is good or not, that actually depends whether that particular move leads you towards the goal or not. So the rewards may be positive, the rewards may be negative. The actions you did, you might get reward instantaneously that may be very well locally, but globally they are not good and stuff like so. And in reinforcement learning, agent basically learns a policy, a plan to do the actions in a sequence to achieve the goal. And that's an optimization problem to solve, and very hard problem. And when it acts, actually it acts in the environment, and environment changes, and it gets the reward and learns. Then at the new state, after observing the new state, it acts again, and then it gets a reward, the observation, and then eventually it moves towards its goal. And maybe the next time the agent went through the same kind of environment and learned through, for example, previous game, that which action which action to perform and which to not. Maybe after second game, get more refined version that what actions in what situations should be done or not, and so on, and moving on and on and on. As the agent plays more and more games, the policy or the planning becomes more and more concrete, perhaps probably to go towards the goal. So this kind of learning is called reinforcement learning. So before moving on, let me just go to Jupyter and show you some examples of this. For example, regression and classification, just to give you a look and feel what do we mean by regression, and in regression what kind of things that we are going to achieve, and what is classification, what do we mean by classification data, and so let's move to Jupyter to just get a look and feel of regression and classification data sets. Okay. So let me just give you a look and feel of what basically this let me just give you a look and feel of this regression data and classification data. What is the format of data, how the data basically appears, and one possibility of how the data basically appears. So let's see a regression data. Let's just get a look and feel. Import some packages in Matplotlib, pyplot as plt. So for example, import this package, import plt pyplot just for plotting the data, because the data just I'm going to show you, for example, is not high dimensional, so it is plottable, viewable. So, and we are going to generate random data, no problem. So that is not some fancy data, that's just random data as SNS. Maybe you need, so Seaborn and Matplotlib, you might be needing those for some plotting. In NumPy is always required, always, when you work in data science. So sns.set, just set the layout. So just import the packages. So yeah, the packages are imported. So let's generate some points. Let's say n is equal to 20. Let's generate some some points, 20. So let's say X is our attribute, some attribute. Let's generate some random data or maybe non-random data. A range, let's say N, and then let's say this is Y that we really want to predict. And the available data has the relationship between Y and X is, let's say that this is 4 times X, 4 times X, let's say minus maybe 9. Let's say this is our data. And so if I just show you X and Y, so if I just print this is X and this is Y. So I want, whenever X is 0, I want Y should be minus 9. Whenever X is 1, I want Y to be minus 5. So based on X, these are the values of Y. So next time I want to just give X and want to predict Y. So because here the relationship is like 4x minus 9, that's the relationship. So for example, if I just plot the data using scatter XY, I can visualize this is what the data looks like, because it is basically a line. It is 4x minus 9. That's a line. In reality, data is not that, that clean. It may have noise in it. So let us just simulate the noise by, let's say, by thinking that there is some noise added when the data was collected, or the noise is there. The data was recorded, collected, or due to any factor, quantization, or maybe any other stuff. Let's say there was some noise that was there, and let's add the noise in the labels and see. The actual relationship is this. That's the actual relationship. But when we record the data somewhere, when it was coming from a network or somewhere, or the sensor recording, there are a lot of sources of noise that is there. So with noise, for example, the data looks like that. Okay, you may increase or decrease the level of the noise here. So once we have this data, our goal, for example, is to give X and predict Y. For example, we want to give X and we want to predict Y. So one way to do that is to just, for example, one way to do that is to do the same stuff using Scikit-Learn, for example, linear regression model. So from sklearn dot linear model, import linear regression. Just check it is imported. Yes. So now model can be linear regression. That's our model. And then what I do is I said, okay, model dot fit. That's a fit function. I'll explain what a model is. I'll explain that in detail. Just I'm going to show you what regression basically is. What a model is, I will explain that in detail in the slides. So X, for example, np.new X is just to get it a two-dimensional array consistent with Scikit-Learn. That's model.fit. Then I can predict Y predict, for example. Predict Y predicted is m dot predict, and I can predict, for example, let's predict all the values. Let's see all the values access. And now what we can do is we can plot the data as earlier, and let's plot what we predict. Let's plot in terms of a line or a curve. So X, Y predict, and what we have predicted, or the pattern that we have grasped, it will be denoted by, let's red color, and a continuous curve. So yeah. So So these blue points, they are the original data, and the red dots, maybe we can have, for example, maybe we can have a scatter plot in place. Rather than this, we may have a scatter plot just to show you that what we have predicted, where is that? So we might have a scatter plot, so plt dot scatter, maybe x, y predicted, and that gives me that. So the blue points, they are the actual points, and these kind of the brown points, these are the points our model is predicting. Once I have this model available with me, I have learned this model. When I call this fit function, actually I did all the training. When I have this model available, the function trained, now I can predict the y value on any x value that was available or not available. So here this x is actually the feature. This x is feature. We have 30 samples of those. We have 20 samples of those. X is a feature. And y is an attribute that depends upon the feature and we want to predict. Here we have synthetically made the relationship between x and y as linear. In reality, in data in any organization, this relationship can be of any form. And finding out the actual this relationship is what we call as finding out the model, or the model selection. Let me also give you a look and feel of, for example, classification problem or classification data. Let me just give you a look and feel of what do we mean by classification data. The classification data appears in what kind of form? So for example, from Scikit-Learn, let's generate synthetic data, samples generator, import, let's use make blobs. Let's import it. Okay, what's the warning? Sample generator module is deprecated, will be removed, and okay, so we can use the newer variant, but that's okay. Okay, now what we can do is x, let's say x and y are the class labels. Let's say x is my data and y is my class labels. Let's say make blobs, that's my function. How many data points I want to make? Let's say 100 or maybe 200. How many classes I want? Let's say 3, maybe. Yeah. So let's say I make this, and then let's check the data, the classification data, how it looks like, using again the scatter plot. Let's say x, that's a two-dimensional data having just two features. I will explain what do we mean by dimension and what are the features. I'll explain that later in the same video, but just I want to give you a look and feel of what do we mean by classification data, what are the labels, and what is that stuff that we are talking about. So c equals y, for example, I can set the color map as autumn. There are several choices, but let's do it like so. Oh, what's the problem? plt.scatter. What's the problem with plt.scatter? There is some problem here. Let me see. The color map is not recognized. Why not? Autumn. Oh, there is an N inside. I just missed an N. Okay. So now that's the classification data. So that's, for example, one category. That's another category. That's another category. We can have several classes. Here we have 3 classes. For example, we can generate data, for example, from let's say 5 different classes, and it looks like so. So for example, this is one category, that's one class, all the data points. Here you can see the features are 2. One feature is x1 axis, another feature is x2 axis. So we have 2 variables, 2 attributes, and then the category label that we want to predict. And the goal in classification is to come up with a model or a function, just like you have seen in like regression model. Come up with a model that when we apply the predict function on that, when we want to predict on the model, it gives us the category label, the class label, rather than this continuous value. So in reality, the data may have several attributes rather than just two, and we will see all that in the upcoming video and slides. So data can appear in several different formats. For example, the data can appear in form of images. So you have a lot of images, and each image is a data point, and you have a label for that image. So images, although the data can appear in images or sequence of images, which are videos, or just an audio signal, which is just a array of numbers and so on, or text. I mean, but the machine learning algorithm, any machine learning algorithm, actually requires every data point to appear in form of numbers. So this number, that number, that number. And these kind of numbers, they are called features. For example, if you see in the case of images, if I just go back to Jupyter Notebook and I show you, for example, if I just show you here the shape of x, so x dot shape, if I just show you that is basically 200 by 2. And if I just show you y, shape of y, it is basically 200 by 1. So if I just plot, for example, x, the very first row of x, so the very first row of x, so that is basically this number and that number. This is the first data point having two features. This is feature 1, whatever that attribute is. This is feature 2, and for the same data point, for example, the category label is 0. I mean, this belongs to class labeled with 0. There are 5 classes and one labeled with 0, then 1, 2, 3, and 4, and 5. Let's, for example, see a data point with let's see the 66th data point or 67th data point indexed with 66, because the indexing starts from 0 in Python. So that is this. These are the features. So feature 1 has this particular value. Feature 1 might be height of a person. Feature 2 might be weight of a person or some other property. And y corresponding class label, if you see, is 0. That's again 0. We might have different class labels. For example, let's say we have 100. That's a data point, and the class label of at 100 might be different, or maybe same. It's all random. Now this belongs to class number 4, which is labeled by 3. So this is a feature, that's a feature. So we have different features, and different data points have different feature values. Now any machine learning algorithm actually accepts this kind of data, which is a lot of sample points and then a lot of features, but all the features, they are numeric. So they must be numeric. In images, for example, you see colors, but there's a quick way to convert those to numbers. Actually, they are numbers, just flatten them out. That's one way. There are other ways. We'll see those in deep learning, that convolutional neural networks, that they use the images as matrices rather than flattened vectors. And there are particular reasons to do that, and they're very good in that case. But even if you want these images in classical kind of machine learning algorithms, there are ways to flatten them in just numeric form. Again, videos can again be flattened into long vectors, or maybe segmented, and then using a technique called bag of words, there are ways to convert the videos again in the vector form. Audio should be converted into vector form. Text should be converted into vector form. There are several ways of converting text data to vectorize the text data. One is to compute the features like term frequency, inverted index, and so on. There are features, and those are numbers. So having a text document, just compute a lot of features out of it and report those features as a vector that represent the text. Other ways of doing that as one-hot encoding. For example, if for example I have an attribute, let's say name, or name, let's say that's an attribute, and one name is ABC, another is DEF, another name is, maybe another person has the same name as ABC, and so on. So I will first see how many different names are there. For example, I have data, there are other attributes as well, name, age, and other attributes as well. So that's a data set. So I will, for example, this particular, let's say, attribute is text type. One way to convert this particular attribute to convert to numeric way, one way is that to just see all different names, and just give, for example, each different name a code. For example, 0, 1, 0, 1. Let's say we have 4 different names: name 1, name 2, name 3, name 4. 4 different names. Then 0001 means the 4th name is present here. So that's 0001, that's a number, and that represents basically, let's say we have 4 names, let's say A, B, C, and D. Let's say we have these 4 names, or any strings. So let's say a D just appear. So we can code it by 0001. Then at somewhere next, B appears. Now the code of B is 0100, and so on. So that way we can convert this text to, and that there are other ways as well, but this is more practical and useful. So the data can appear in several formats. We have to convert the data to features, and the features are numeric. And once they are numeric, consistent, and then we can move on. One more thing, converting data to features or numeric is one step. The other step is data standardization, and it is much more fruitful to scale all the attributes of the data to a common scale and normalize all of them, make them share a particular center. And this technique, actually data standardization, sometimes divided into several key steps, but most key step is data scaling or attribute scaling and data centering. It actually gives most of machine learning algorithms a boost up to achieve the objective function quickly as compared to otherwise. So once you have data in any kind of format, the first thing to do is to convert them to features. A preprocessing step data standardization may be applied. Once that is given, then you are good to go to select a model. What a model basically is a function. Model is just a function in the feature space. What a feature space is. So for example, let's say if we go back to Jupyter again, our feature space is 2-dimensional here. You can see this is our feature space. We have just 2 features. Let's say the first feature is height, and let's say the second feature is some other feature. It is negative, but let's say it's weight. Negative weight represents something, or maybe another good feature. So feature 1 is, let's say, F1. Feature 2 is, let's say, F2. Now you can think your data as so for example, let's say the first data point x1, let's say, has value 2.4, let's say, and the second feature value is, so this is the first feature value, the second feature value is, let's say, 0.7. We can think, and then we have another data point, another sample with first feature value as, let's say, 10, and second feature value as, let's say, 1.7, and so on. We have 20 these data points. What do we mean by feature space is that, let's say you have a space where this is x1 axis, and this is let's say f1 axis, feature 1 axis, might be height or something. That's feature 2 axis. So the first feature is f1, let's say. The second feature is f2, attribute or features. So in this space, for example, this is completely defined by f1, feature 1, and feature 2. This x1 really is a point. For example, if I move 2.4 units in feature space in axis 1, and then I move, for example, 0.7 units above, then this particular point is x1. And I can color that point as blue if it belongs to class 1, and red if it belongs to class 2. Another point another point, for example, x2 has feature 1 value as 10, maybe here, and feature 2 value as 1.7, maybe here, and that may belongs to class 2. So each and every data point is each and every data sample basically is a point in the feature space, maybe negative value and stuff like so. Okay, so that's, I mean, all these blue points belong to class 1, for example, and all these red points, they belong to class 2. But at the end of the day, each sample is a point in feature space. So what a model is, model basically is a function in a feature space. For example, if I'm doing classification, for example, that's a classification data, my function might be a curve that separates out one class from the other. For example, my function might be this, maybe. Maybe this. So, like so. I mean, that's not a good choice of the function, but it might be all the, or basically it goes like this. That's a better way. So this, and let me redraw it. So let me redraw it in a different color, maybe to, yeah. So green. So let's say this green is my classification boundary or a function that actually all the points that are below or in one side of this boundary belong to class 1, all the rest belong to class 2. But that at the end of the day is a function. It's a function that depends upon f1 and f2. It's a function in the feature space. And as you have seen, just let me go back to Jupyter. As you have seen in, for example, linear regression model, if you go back, the function here that we have taken is basically, let me show you this function without noise. For example, you can see that function is y equals so y equals a function of x, and that function basically is, let me define that function as f of x is basically 4 times x. For example, that is 3x plus 4 or plus maybe 6. In this case, that is also a function that depends upon x. That's also a linear function, but the parameters now are 3 and 6. So these are called parameters of the function. So, but either way, a model at the end of the day is a function in feature space, and function normally has a lot of parameters. So feature space, the total number of attributes are called the dimensions of the data. For example, in the previous example, we have 2-dimensional data. Because we have 2 features, we might have many more features. If you have more features, we may not be able to visualize it, but we can have many more features. Let me show you a data set, a classification data set with several features. Let me show you that just to get a look and feel of high dimensional data. Even though that high dimensional is not that high dimensional, but let me show you let me show you 4-dimensional data in which we have 4 iris data that is available in Seaborn. So load, that is available as a built-in data set, iris. Let's say that's data. Let me show you that data. Iris dot head. Let's say 10 data points. Oh, what's the problem? There is some problem. Wow, where is the? I guess I get some problem here in loading that data set. What's that problem? Iris.head sns.load data in dopen traceback. What's the problem? Where is the problem? Maybe I'm able to trace that problem. So hold on with me. Let me trace that problem. URL open error, so that data might not be. So SNS load data is not available. Why is that the case? So yeah, it should be available. It should be available. Load data set. Maybe I have done some mistake. Oh, I guess I have to include. I have to load the pandas library as well, because I'm using the SPD. I guess I have to do that because I'm using this head function, and that might be there in pandas. Maybe that's an error. Oh no, the error is still there. So what should I do? I guess I should, let me generate some data for you, high dimensional data. Why not? Let me generate a synthetic data for you. Although it should work, but let me generate a synthetic data. So for example, let's say X is np.random. Let's say rand, just to give you a look and feel. Let's say 200 samples, and each sample contains 4 elements. Let's say that. So now if you see the shape of X, and let's say Y. Let's say Y is np dot zeros, let's say, and let's say that is 200 by 1. np dot function may have a lot of parameters, yes, but there is another term, for example, which is called the dimensions. Dimensions refers to the total number of features of the data set. For example, the data that we are just working with has 2 features. So 2 features like F1 and F2, these are 2 features. In that case, the dimensions of our feature space is 2. If, for example, we are working with data with more than 2 dimensions, let's say we are recording a lot of attributes, that normally happens. Normally the real data sets has a lot of dimensions, a lot of features. Then the dimensions of data set basically means the number of attributes of the data. Where the where the dimensions refers to the data, the parameters normally refers to the function. So for example, we have a function f of x, and let's say that function is 3x plus 4. Let's say somebody told us that the model basically is some function, and that function is linear. Let's say that's really difficult to know that the relationship of x and y that is linear, or the relationship between a lot of attributes to the target attribute or the label is linear. If that is linear, then the linear function, for example, in 1 dimensions, let's say we have only one feature x, that has this particular form. Now we call this a as a parameter and b as a parameter. But there is one parameter on top of that, that is our model class is linear. Who told us that the relationship indeed between x and y, that is y? Who told us that the relationship indeed is linear? Well, if we assume it linear, then we can estimate these parameters, what are the best parameters, because even if it is linear, what are the parameters? Because if I change the number 3 to some other number and 4 to some other number, that function is still linear. That relationship is still linear. But what are these parameters? What are the best parameters that actually describe that relationship? Well, these are parameters, and to find out parameters, we need to first specify the model class. Because if the model class, for example, is linear, then there are a lot of linear functions inside that model class. All they vary with the parameter values. For parameters 3 and 4, that's one linear function. For parameters, for example, -3 and 9, that's another linear function, and so on. So, but that depends upon believing that the relationship is linear. If the relationship, for example, is a 2-degree polynomial, then the shape might be this: ax squared plus bx plus c. That might be a shape. That's 2-degree polynomial, for example. Now, even in 2-degree polynomials, there are a lot of polynomials, actually infinitely many, depending upon what parameters are the best. Now, one thing is to select the model class. Selection of the model class is also a parameter. What model class will be there? But that parameter is called hyperparameter. That must be known. That is not that parameter is not trained. That is not learned. That is somehow injected in. Once the model class that is one kind of parameters, hyperparameter. There are a lot of others. Remember, the hyperparameters are the parameters that are not learned through training. They are somehow adjusted with other processes, or maybe some beliefs, or maybe hit and trial and stuff like so. Now, once we know the model class, then, for example, linear, then we have what parameters in the linear. What value? What should be the value of A? What should be the value of B? If it's a 2-degree polynomial, then what should be the value of A? What should be the value of B? What should be the value of C? Parameters. So we first set the model class. For example, 2-degree polynomial, for example, that's our model class. We believe somehow that the relationship between x and y is a 2-degree polynomial parameterized by these. Then what we have to do is all our predictions, y predictions, for example, it is basically y prediction is on a particular test point, is on a particular point, let's say x new, let's say x new, that's our prediction. But how to train our model? How to check, how to get these values A, B, and C? Well, one way is to get A, B, and C such that the predicted values, let me call them as y hat, the predicted value of every sample is the same as the actual value, the actual label of that sample. That's one way. And just check this. One way to just check that whatever parameters that we come up with, are they making a lot of errors on available data, which is called the training data? How to check how much error they are making, and what do we mean by error, by the way? So one notion of setting up the error is, for example, this is if this is the actual label of the ith example, or actual value of the ith example, and this is our model is predicting on the current parameters, then one way to model the error is just take the difference. But we have to take the error on all the training set, all the training data. For example, in our case, if we go back to Jupyter, in our case, we have 20 data points. For regression, we have 20 data points. For classification that we generated, we were having 200 data points, for example. So for all data, we need these parameters. We need these parameters A, B, and C. They should be found such that they should perform very well on all the data points. And by very well, I mean they should not be doing errors. Okay. And one way to model the error is to just take the difference. But then the problem is the difference sometimes might be positive, sometimes might be negative. So, and you are summing up all errors on all the examples. If this is the error on ith example, then if you sum up all the errors, then maybe negative errors, they may cancel out the positive errors, and you get the overall error minimum, 0. However, each example has an error. One way to model that is to take the squares, or maybe absolute value. The square is a differentiable function. It has properties that leads the optimization algorithm to work in a stable form, for example. So in place of absolute value, people actually prefer to use the square, and the square actually just focus on the magnitude of the error rather than the sign of it. So this particular error is called the squared error, the total squared error. And if you average the squared error on the total number of examples. That is called the mean squared error. And that might be one criteria. For example, I want my parameters A, B, and C such that the mean squared error is as minimum as possible. So having that said, basically, I may impose the problem as such: find A, B, and C. Remember, we have fixed the model class to be, let's say, a 2-degree polynomial. Find A, B, and C such that MSE on the training data is minimum. So if MSE, the mean squared error, and by the way, this mean squared error is one way of measuring error, one way of modeling error. Error is sometimes called cost, or error, sometimes called risk or loss. There are so many equivalent kind of names. So, and this is one way of modeling the error. There are several others. Each have its own properties, benefits, and the problems associated with that. Now, the optimization basically is a procedure to find out these parameters A, B, and C. So remember, we have set our model class. Let's say the model class is 2-degree polynomial. Then we set our cost function. What is the objective that we want to achieve? Well, we want to minimize the mean squared error on training data. Okay, the objective is set, the model class is set. Now the optimization routine actually is a routine that finds out the parameters A, B, and C, the values of A and B and C, that actually minimizes whatever error function or cost function you supply or you set. If I go back to Jupyter just to give you a look and feel of what actually I'm saying, what do we mean by optimization routine here? This actually fit function, if m dot fit, this fit function actually finds out, this fit function actually applies an optimization routine that gives the best parameters. And let me just see the best parameters if I can here. Let me just walk through this again, and let me just show you the parameters that I have now. So let's say this, and let's say Alt Enter. Let's just write M and see whether what is those things inside M. So for example, M dot fit intercept get parameters, and let's say we apply this get params and see what happens, copy of X and stuff like so. So I mean, there are a lot of parameter values that are there in this model. Once we fit those values can be displayed here. What is the value of, for example, what is the value of, after fitting, what is the value of parameter, what is the value of the first parameter that we came up with, what's the value of the second parameter that we came up with. So yeah, so this optimization basically is basically a routine that give rise to the optimal values of A, B, and C, or whatever the parameters is. And there are several optimization routines. Which optimization routine to cover, it depends upon what was the model class, what was the error function, and a lot of other stuff. And then there are a lot of optimization routines, and maybe one may be better than the other. And in several cases, we do not know which routine is the best. And in that case, the optimization routine, selection of the optimization routine may also become a hyperparameter. So, but after setting the model class, after setting the objective or cost, we just apply an optimization routine and get the parameters. Once the parameters are there, now we can apply the predict function, and we can predict all the labels using all the labels, whether they are regression or classification, using these parameters. Okay, so the problem here, the very powerful kind of problem is overfitting. Overfitting is a problem that, for example, if you want to learn all the data, for example, in regression, for example, you want to come up with a model you want to come up with a model that actually passes through all the data exactly. So here, for example, in this case, you can do that. You can create, for example, with linear model, you do not have a flexibility. Linear is just a line and it will pass either this way or that way or stuff like so. If you, for example, allow your model to be 2-degree polynomial, 3, 4, 5, 6-degree polynomial, it will be much flexible. And to optimize or to minimize this mean squared error, for example, or any error on training data, your optimization routine will try to fit the function, fit the model that passes through each and every data point, because that will lead to the minimization of the error. But that actually leads to overfitting. Well, overfitting means you fit the data or you learn the data so well, the training data, that it cannot generalize onto the unseen data. Actually, you put all your effort on training data, actually you memorize the training data, and you do not know what to do on the upcoming or the new problem. And that problem becomes really problematic when either the data is in small amount or small quantity, or the data has a lot of noise. Either way, I mean, even the small data, the amount of data to be small is also referred to as a particular form of noise. So if the data is noisy, which means it is either small, you have only a few samples available, and the term only a few is relative to your model complexity. So if you have only a few data points available, and you fit a very powerful model, very flexible model, very high degree kind of model. A flexible, powerful model can be designated as a model with a lot of parameters. A model with, for example, a 1-degree polynomial or a linear model was having 2 parameters, remember? And a 2-degree polynomial has 3 parameters. So a model with more effective parameters is referred to as more flexible. And more flexible models tend to minimize the error, thereby actually overfitting on training data. And due to noise in the data, it actually fits the noise and may not generalize very well. So for example, this is not a better curve. This is better, for example, and this may not be better. So there are levels. Underfitting means you actually miss the training data. You could not fit the training data at all. Overfitting means you fit the training data so well that you are unable to generalize because it fits the noise as well. Balance is something, or just right is something that is between underfit and overfit. You can always minimize the cost on training data by having a flexible model, by get a model with more parameters, allowing more flexibility, and it will pass through each and every data point. Exactly. But that's bad for generalization. Let me show you a simple example in Jupyter Notebook where we actually try to fit a polynomial of higher degree in our data and see how that passes through each and every data point. So for example, let me just generate some data points again, like where we have generated the data points. Let's say we have some data points generated like so. So let's say here, let's say we have some data points. Okay, we generate them and we plot them. Okay, let's say these are just, let's say 20 of them. Let's say these are 20 data points. Okay, and let's try to fit a model that actually passes through each and every data point. First, let's try a linear model that passes through this. We already have done that, but let me just pick that up again and see what the linear model does with it. So if we just see that, the linear model, or maybe we plot it like plot, and we get this line, maybe in red. Maybe the color should be red. Red. And here you saw that this is the data, and that is a 1-degree polynomial or a linear model with very few parameters. So not that flexible. Let us now try to fit in the same data set. Let's try to fit a model with, let's say, very high degree polynomial, let's say 20-degree polynomial, why not? Let's fit that. So what we do is we compute the polynomial features. We first have to import, for example, from preprocessing, we have to import certain things. For example, from Scikit-Learn dot preprocessing, import polynomial features. So let's import those, and after having those features available, let's convert our data or fit the high degree polynomial in our data. For example, let's say we fit polynomial features equals to, let's say that's our model, polynomial feature model. Features. Let's say we define our degree to be, let's say 20. That's a high degree polynomial, very, very high degree polynomial. Then x, let's say x poly features, or x with respect to that is pf dot fit transform on x. And then what we do is we set okay, okay, let's say for example, again we set another model. Let's say model 2 is again linear model. It's again a linear model, but the linear model on polynomial features, which that's a linear model, linear regression, let's say. And what we do is, so what we do is m2 dot fit. So here we have to add the new axis term here, just to stay the dimensionality consistent way. New axis, that's x poly. Then we have linear regression model. Then we have fit, let's say x poly. And the y labels of y's are same. That's our m2. And let's say y pred poly is m2 dot predict, let's say, and we predict that on x poly, and we get y predict poly. And let's plot that curve as well and see what happens if the code does not have a bug. Then let's see what happens. I've just actually fitted a fitted a 20-degree polynomial to my data rather than just a 1-degree polynomial, just to show you the impact of blue or green. Maybe if there is no error, then things will work very well. So now you can see that this green model, it actually tries to go through each and every data point, and tries to go through each and every data point very clearly. I mean, it goes there and there and there and stuff like so. It will be more evident. Let's for example take the example with a few points. For example, let's just take 10 points, and that's this, just to stay the numerical stable, having the numerical stability, and then just have this, just 10 points. That will be shown in more, the numerical stability will be shown in a better way. Now you can see this green curve, it is passing through each and every data point. And even if the data point is noisy and goes like there, it will try to go there and fit that. But that's bad. I mean, if you're going to fit your training data exactly in this particular case, your error is small, but the pattern you got is a weird pattern on the new data set, you're going to make errors. And that's precisely what do we mean by overfitting, and that's a bad idea. There are several ways to avoid overfitting. I mean, one way is to just add a regularizer, and well, one way is always to gather more data, but that is not always possible. So a practical way of avoiding overfitting is basically to add a regularizer, which is called the regularization. Regularization means you set up your optimization routine in such a way that the magnitude of each parameter is not that large. So if the magnitude of your parameters is bigger and bigger, higher and higher, then you may stuck in a problem that you may be overfitting. So if you restrict your optimization routine to come up with the parameters that minimize the training error, as well as the magnitude of the parameters or the absolute values of the parameters, they are not higher. In that case, it can be shown very easily that the flexibility of the model can be reduced, and you can avoid overfitting. This overfitting is a big problem, and there are a lot of methods to deal with it. So one good way is to always choose a simple model, a model with a few parameters, but that may underfit, that may not actually get any pattern. On the other end, if you choose a very complicated model, it may overfit. The balance in between is you choose a complicated model, but then restrict the parameters to get small values, so that the flexibility can be restricted, just like you have a high-speed car, and but you're not allowed to. Think about it. You have a high-speed car, and you're not allowed to speed up the car with a full speed. There are automatic brakes if you speed up the car. There are automatic brakes that are there, and it reduces the speed of the car. So that is that has resemblance with this overfitting. A high-speed car is resembled to a model that is basically high-speed car is just a model that is more flexible, having more and more parameters, and brakes are these regularization terms. So yes, so this overfitting is there. So do not try to minimize the error only. Do not just focus on that. There are a lot of other things to focus. Okay, so I end my video here. In the next video, we are going to talk about generalization and validation sets, some cross-validation and stuff like so. We are also going to discuss about the data snooping, what are the test sets, and so on. I'm going to discuss the relationship between probability distributions with this with the dimensionality of the data. What are the link between probability distribution and stuff like so. And then I will be discussing a general pipeline of any machine learning algorithm that we should move on. Not only that, I'm going to discuss the deep learning, the famous frameworks of deep learning in the next video as well. And with deep learning, I will be trying to actually give you a hands-on project using Scikit-Learn, a full hands-on project. So let's code in Scikit-Learn. Let's code along with all these concepts like data snooping and probability distributions and all that stuff. Along with that, let's code, for example, a face recognition application in the next video, whole code from scratch. So we will be writing all the code. We will be doing one project in the next video, that is face recognition project, along with deep learning concepts, along with data snooping, generalization, cross-validation, and probability distributions and curse of dimensionality and this kind of stuff. So there is more to come in the next video. If you like this video, for example, in this particular video, I just discussed the very basics, a few of those. A lot has to come in the next video. But these are just the basics. I tried my best to convey all these terms in as simple ways as I could. If you like our content, please do subscribe our channel. Press the notification button so that you can get the notifications for our new videos that are upcoming videos. Also like our content if you really liked it, and share it with others. Okay, so hope to see you in the next video.